1, 2, 3. 1, 2, 3. 1, 2, 3.
Hey guys, what are you doing?
Oh, hello. Got a friend over here. Who are you?
I'm Kevin.
Oh, that's nice. I'm Yoav.
I'm Matt. I guess we ought to play a new game, huh?
What do you suggest?
How about some blackjack?
I could do that. I'm a
Yeah, sure.
novice. I'm a novice, so let's play for low stakes, okay? Like, say $1,000?
It's a deal.
All right.
Let's see who wins.
All right, deal me in.
Want a card?
Okay, hit me.
What are the rules again?
Well, you try and get to 21. Anybody gets to 21 wins. If you go over 21, you're going to lose.
Oh, I see. I don't know. I guess I'll
want a
save.
card?
No, I guess I'll save
Stick?
what I have.
I'm going to take one more. I'm over.
All right, I'll stay.
So what happens now?
Well, you guys figure out who's got the most.
All right, I've got 19, Yoav.
Oh, what do you know? Look what I got. I got 21.
Ah, blackjack.
Wait, I think there's some other people watching us here. We ought to introduce ourselves a little bit more formally.
All right, I'll start. I'm Kevin. I'm an associate professor of computer science at the University of British Columbia in Vancouver, Canada. My research is on artificial intelligence, game theory, electronic commerce, and algorithms.
I'm Matt Jackson. I'm a professor of economics at Stanford University, and I do research in game theory and social networks and a variety of microeconomic topics.
And I'm Yoav Shoham. I'm also a professor here at Stanford. Like Kevin, I'm also a computer scientist in artificial intelligence and electronic commerce and game theory. And we're here to co-teach the class on game theory. So maybe let's start by saying a little bit about what game theory is about and as importantly, what it's not about. So often when we think about games, we do think about things such as rock, paper, scissors, or poker, or sports games like soccer and baseball. But really, game theory is about all kind of strategic interactions among self-interested agents, including those frivolous ones, but also much more serious ones. Matt, you're an economist. Tell us more about serious games.
Sure. Game theory has become a really essential tool to understanding a lot of different interactions, anything from auctions to people's behavior in financial markets, to even to international conflict, to understanding political interactions. So it's become an essential part of any social scientist's toolbox. And indeed, it's actually used even beyond that. So things like biology, predator-prey games, a whole series of things. So it's really a fairly widely applicable thing in any situation where there's competition, strategic interaction. So there's a lot to cover here.
That makes sense. But now, Kevin, you and I are computer scientists. What are we doing here?
Well, these days, game theory has become a really hot area in computer science, basically for two reasons. First of all, computers are increasingly a way of bringing people together. And that means we have to think about how people interact when we bring them together. And that's true whether you think about networks, keyword auctions that form the basis of almost all of Google's revenue, peer-to-peer file sharing systems, or consumer sites like eBay or TripAdvisor or Yelp. To understand how any of these systems work, we really have to think about how their participants are self-interested and how those interests drive their behavior. The second thing is that the sorts of economic settings that game theoretic economists like Matt study, as they scale up and get bigger, they start to encounter computational dimensions. And to make the right kind of sense of those and bring these things into practice in the real world, it's really necessary to think about them in terms of algorithms, complexity theory, and artificial intelligence.
So let's speak a little bit about our class. First, let's set expectations. For all these potential applications we're discussing, our class would really be very fundamental, about the very fundamental modeling tools here. We will not attempt to advise people on how to use it really in the real world in any direct way. We'll only use examples by way of illustrating the the formal constructs. So let's speak a little about the syllabus.
Sure. So the course will run about 7 weeks. It's really an introductory course. It doesn't presume that people have any experience in game theory before. It'll assume a tiny bit of background and probability and calculus, but generally it should be accessible to a pretty wide range of people. Our intention is just to show people how our game's structured, how do we think about strategic interaction between people. We'll start with equilibrium notions, we'll talk about incomplete information, we'll talk about timing, repeated games, we'll also talk about coalitional structures. So we have quite a bit of things to cover, but it should be a very fun course for it.
Kevin, you want to speak a little bit about some of the mechanics and what people need to do and so on?
Sure. So there's a lot to this course besides just the videos. Some of these things are going to be graded and others not. So on the graded side, there are 3 key components. The first are quizzes that happen after the videos that you can use to test your comprehension. And if you find that you get some of the questions wrong, that might indicate to you that you should go back, see the video again, and make sure that you know everything you need before you proceed to the next material. The second element is discussion boards, which you can use to ask questions about parts of the course that you're finding confusing, and also to raise logistical questions about the course. And those discussion boards will be answered by other participants in the course, by teaching assistants, and also by Matt, Yoav, and me. The third element is lab exercises, where you can optionally play some of the games that we actually introduce in the course, see how you would reason in these games yourself, and then we'll have chat rooms as part of the labs where you, in real time, you can actually talk to other people from the course, share your experiences about what you learned, and see what they have to say. On the graded side, we'll have weekly problem sets, which will be sort of like the quizzes, but in a bit more detail. They'll give you a chance to show what you learned from the material in that week. And we'll have a final exam that will cover the whole course. Each of these you can take only once, and as I said, they'll be graded. We'll use that grade as the basis for your certificate of completion. So if you get all the way through the course, you'll get a certificate that's signed by all 3 of us.
So, and that will be a total of about 7 weeks, as we said. We should also mention that this is a very large class. There's many tens of thousands of students here. So we will do our best to be clear in our presentations, but a lot of this will involve help among the students themselves. So there are online forums, and they're an essential part of the class. You really want to form study groups to consult each other on the problem sets, on the lectures. We do have TAs that will monitor the forums, both TAs at British Columbia and at Stanford, as well as community TAs that have stepped up. But at the end of the day, it'll only work if, as a community, we all work together. Please, because of the large numbers, don't send us personal email. It's not that we don't like to speak to you, we just won't be able to handle it, so we won't be able to respond. Similarly, there is the class website on the class website, as well as on the social media. If you want to kind of follow us personally on our personal sites, by all means, but no, please, friend requests and so on. Again, the numbers are so large, we won't be able to respond. This is really going to be a fun class, isn't it?
Oh yeah, I'm looking forward to it. Should be a great time.
I had a lot of fun with that previous game.
Yeah, and actually, I think it's time for Kevin and I to win some money back.
Well, let's see how good you are.
Okay.
Welcome to our advanced course on game theory. This course covers the topics of social choice, mechanism design, and auctions. And essentially, it asks the question, if I know that agents are going to behave game theoretically, how can I design interactions for them that lead to good social outcomes? The first topic we're going to think about is called social choice. And here, leaving aside the question of strategic behavior, we ask about how to aggregate different people's preferences together in a sensible way. I'm Kevin Leyton-Brown. I'm from the University of British Columbia. My co-instructors, who you'll meet in subsequent videos, are Matt Jackson and Yoav Shoham from Stanford University. Let's get started. So social choice is essentially the problem of voting. And the first thing that you might think is that voting seems like an incredibly simple thing to study. How hard can it be to study something that, after all, involves just filling in one of the boxes out of some small set of different candidates? Well, I want to argue that voting actually is tricky enough that we want to have a mathematical theory of it. Here's an example. In the year 2000, the US presidential election came down to who won Florida, and it was incredibly close. After complicated recounts and an appeal to the Supreme Court, George Bush turned out to be the winner by 537 votes. However, Ralph Nader, a third-party candidate with a pretty limited amount of support, got 97,000 votes. In surveys that were taken after the election, it turned out that about twice as many Nader voters would have chosen Al Gore instead of George Bush if Nader hadn't been a candidate in the election. Now, leaving aside whatever preferences we might have about who should be president of the United States, this seems like a bad outcome, because it seems like more people overall preferred Gore to Bush in Florida, and nevertheless, Bush was the winner. So it seems like we didn't do a very good job in this election about taking everybody's preferences into account and selecting the right winner. Indeed, recently there have been popular movements around the world demanding new voting systems. Here I'm showing protests in London and in Ottawa by British and Canadian citizens who think that they should have new voting systems that do a better job of taking their whole preferences into account. In this week of the course, we're going to ask whether it's really true that there are other voting systems that are better, and what better actually means. So we're going to start by looking at different voting schemes, seeing how they work. We're going to see that each of these voting schemes is sometimes able to give rise to kind of paradoxical outcomes, where it seems like something wrong can sometimes happen. And we're going to culminate in a famous proof that shows that in a really formal mathematical sense, it just isn't possible to avoid these kinds of failures. So thanks for joining our course, and look forward to having you for the videos to come.
Hi folks, this is Matt, and so we're talking a little bit about social choice theory now, and I'll introduce you to voting schemes and social choice functions. And in terms of the overall idea, what we're looking at now is we're looking at a setting where a society is making decisions, and we've got a bunch of different individuals who have preferences, and that we want to sort of aggregate those, right? So we've got a set of voters, a set of people, they have to make decision, and we want to take into account the preferences of the different individuals. So we're looking at a setting where we have a set of outcomes or a set of alternatives. So something we're going to choose over, so it could be a set of political candidates. It could be that we're trying to choose a set of new members for a society, that we're trying to decide on a new tax rate for government. We've got a whole series of different questions, and there's possible outcomes that are there. And the people, the voters, the agents, the people in the society have preferences over these outcomes. So in this setting we're going to look at, for now, people are going to have preferences. They'll be able to tell you, this is my favorite outcome, this is my second favorite, my third, my fourth, and so forth. And what a social choice function is going to do is take the preferences of the individuals and, as a function of those, tell us which outcome are we going to choose. So it's going to be a mapping from profiles of preferences to a particular outcome. And generally what we're going to be interested in is sort of which of these social choice functions would we like to have. Now, in the course, we're going to eventually have to talk about incentives, because people, in a setting where we're voting for a bunch of candidates, it might be that and you ask me which one's my favorite candidate, I might not tell you truthfully which is my favorite candidate. I might vote for somebody else if I think my candidate has no chance of winning the election. So people might try and manipulate the voting scheme by changing how they represent their preferences. They'll say, okay, I would like to vote for this person, not for this other person. So we'll have to very carefully think about how the mapping from preferences into alternatives eventually is achieved. But for now, what we're going to do is we're just going to look at the function itself and say, okay, if society, there's a set of ways in which these things can be mapped, and then later we'll ask which ones can actually be achieved or how they can be achieved and so forth. Okay. So given is a set of preferences or outcomes or alternatives. So that's going to be the set O. And people are going to have preferences over these, and we're going to represent these in a very simple form. Generally, the agents are going to have strict preferences over these things, so we'll eliminate indifferences that will make our life easier. So that's going to be represented by this relationship, which is going to be generally linear orders. So we'll look at situations where people are not indifferent, so they'll be having a linear order or what's known as a total order over the alternative. So they can tell you which is my favorite, which is my second favorite, and so forth. So given a finite set, I can just list them in order. And so a linear order, the set of linear orders will be denoted by L, and those are going to be the binary relations, which are total and transitive. What does that mean? That means if you look at any two alternatives, any two outcomes, A and B, that are not equal to each other, then either A is preferred to B or B is preferred to A, but not both. So it means, first of all, I can tell you which of the two I prefer, and I'm not indifferent. Okay, so one part about a linear order is it's going to be a strict ordering. I'm never going to be indifferent. And for any two alternatives, I can always make a comparison. I can't say, I don't know, I'm not sure, I'm not undecided. All these voters are decided. They can tell you exactly how they rank everything, and preferences are going to be strict. They're also going to be transitive. So if I like A better than B and B better than C, then I better like A better than C. Okay, so we've got a nice transitive ordering. That's going to be a linear orders, total, and transitive. Sometimes we'll also be working with non-strict preferences. So it could be that someone's indifferent. So then we'll allow for transitivity and completeness. You can make a comparison between A and B. So A could be weakly preferred to B, B weakly preferred to A, and you could have both relationships holding at the same time, which means you're actually indifferent. So sometimes it'll be better to work with non-strict relationships. And in fact, when we're thinking about how society decides on a relationship, it might be that everybody in a society has a strict ranking, but then society as a whole ends up with a weak ordering. So we'll allow for non-strict preferences as well. Okay, so those are going to be preferences. Those are the objects that we're going to assume people have, and then based on those, we try and make a choice for the society. Okay, so the formal model then in terms of the way that we'll work through social choice functions, we've got a set of individuals, finite set of individuals, finite set of outcomes, O, and we'll consider the linear orders on the outcomes, this set L, and also the non-strict version. So social choice function is going to be a function which maps from the set of preferences, weak preferences, into outcomes. So if you tell me what everybody thinks in the society in terms of their rankings, I'll pick an outcome. So a social choice function tells you, as a function of what people believe in terms of their preferences of different outcomes, what's the outcome that we're going to choose. A social welfare function or a social welfare ordering is going to be the same kind of object, except that instead of just picking an outcome, what it's going to do is actually say, give you a full ranking of outcomes. So society is going to rank outcomes. Okay? And that's different than just picking an outcome. So it might be that we've got 3 outcomes A, B, C, and we ask people what their preferences are over these things, and we're going to pick one of them. So we just need to make a choice for who's going to be our president. Alternatively, we might actually want society to be able to rank these objects. Okay? So often when you look at rankings of organizations, like rankings of universities or rankings of schools, we'll take a whole series of different people who say, here's my ranking, and then we aggregate those up and say, okay, here's an overall ranking, and there might be ties. Okay, so we might have people express their preferences or their rankings, and then society might end up saying, here's society's rankings. Okay, and that's different. So sometimes we're picking an outcome, sometimes we're picking a ranking. Okay, so what are some examples of these things? The most basic and most widely used is what's known as plurality rule. What's plurality rule? That's just picking the outcome that is most preferred by the most people. So everybody just gets one vote. They get to express it, and generally, if we'll assume that people are truthful, we'd assume that they'd express who's their favorite, and then the social welfare, social choice function just picks the outcome that is most preferred by most people. So that's known as plurality rule. Cumulative voting, that's another interesting voting rule. You give people multiple votes. So you get a set of votes, and you can give your votes to different candidates. So if there's 4 different candidates, I can assign several votes to the first. I can give 2 to my most preferred, and then 1 each, say, to my second and third. And then we'll count up and find who has the most votes. So now I've got multiple votes I can express. Approval voting is another interesting voting rule. And that's one where you can basically just express whichever outcomes you like and not express which ones you don't like. So this is often used in saying electing new members to a club or electing new members to a society, something like that. So you can, like a Hall of Fame, you can list which candidates you think should be included, and then give zeros basically to the ones you don't think should be included. So you just vote for the ones you think should be included, not for the ones you don't. And then there's some method of counting up and either picking just one if we just are going to elect one candidate, or picking several if we're going to pick memberships. There's some threshold. And so that's known as approval voting. So these are different methods of making choices, and they're going to have different properties. A set of other voting schemes based on more kinds of information ranking. Plurality with elimination. So what's known often as instant runoff, or single transferable vote, or transferable voting. It goes by a series of different names. And in that case, what one does is you actually express your whole preference ordering. And so we count everybody's favorite outcome. So think of everybody voting for their favorite outcome. And if some outcome has a majority, it wins. So if somebody gets more than 50% of all the votes, then it wins. But if nobody has a majority, so if we have, say, 3 or 4 outcomes, it could be that we have some candidates that are tied, or no candidate got more than a majority. And so what we do then is look at the outcome with the fewest votes and eliminate it. Okay, so knock out the one that has the fewest votes. You may need a tie-breaking procedure to, if there's 2 that have the fewest votes. So knock the one with the fewest votes out, and then re-vote. So now we've only got a subset of the candidates left. Everybody expresses their favorite out of this. If somebody has a majority, that's the winner. If not, knock another one out. Okay, and so forth. And actually, there are rules. There's variations on this. The French presidential election works this way, where you first vote, and then if nobody wins enough votes in the first round, then there's a runoff among a subset of candidates. There's a number of systems that work this way. Okay, another one that's very interesting and widely used, what's known as Borda rule, Borda count. How do we pick outcomes under this? In this case, you get to give your ranking, and so you're assigning a single number to each outcome. And so generally, if I suppose I have a ranking of I like A better than B, better than C, better than D. If we had 4 different possible outcomes, what I would give is I get to give a score of 3 to my preferred, 2 to my second preferred, 1, 0. And so my most preferred gets 3 votes. This gets 2, 1, and 0. And now when we look across different individuals, we add them all up, right? So somebody else has D, B, A, C. Somebody else has B, C, A, D, etc. Right? So in this case, D gets 3, 2, 1, 0. B gets 3, 2, 1, 0. So B gets 3 votes here, 2 votes here, 2 votes here. B is going to have 7 votes overall, and so forth. So Borda count will get numbers for each one of these things. Then we count up this total number of numbers, and the winner is the one with the highest score. And this is actually going to produce a social welfare ordering, right? It's going to tell us which outcomes are in first place, which ones are in second place, and so forth. So it's actually going to rank all the outcomes. And so board count gives us an overall ranking. And actually this is used in a lot of sports evaluations. So in the US for ranking basketball teams or football teams in different polls, in a series of different situations where you're trying to rank alternatives, you can give votes and then aggregate those up and produce a ranking. Another one that's very interesting, successive elimination. You order the alternatives, and then you first have a vote over the first two. Do we prefer A or B? The winner of that gets matched against C. The winner of that gets matched against D. The winner of that gets matched against E, and so forth. So you order the alternatives, do a pairwise vote, and then do this. This actually works often in legislatures, where we could imagine that there was a bill introduced, then somebody amended the bill, then somebody put an amendment to the amendment. And what we would do is first vote whether we do the amendment to the amendment or just keep the amendment. And then the winner of that gets put up against the bill. Do we want that versus the bill? And then finally we ask bill, no bill. So that's voting by successive elimination and is often used in many legislative processes. So you can see there's many different ways of voting and choosing alternatives. And these are all going to have different properties, and that's what makes this area so interesting. There's not a simple way to do things. There's many different ways to do things. They're each going to have pluses and minuses, and so there could be trade-offs involved. Now, one important concept that we'll be talking about a little bit in the future is what's known as Condorcet consistency. And Marquis de Condorcet defined this centuries ago. And the idea here is looking for a candidate that's preferred, that beats every other one in a pairwise majority. So if you look, if we've got A versus B, A is preferred to B by a majority. And we look at A versus C, A is preferred to C by a majority. And A to D, so if A beats every other alternative, it has a majority of votes versus all other ones, then that's known as a Condorcet winner. Okay, so it's something which majority prefers to any other alternative. And when those exist, then we'll say that a rule is Condorcet consistent if a social choice function picks a Condorcet winner when there is one. Okay, so that's a nice property that's sometimes desired of a rule. And there can be a cycle. So for instance, if we had three alternatives, person one likes A, B, C, person two likes B, C, A, person three likes CAB. Now you can see here A's preferred to B by a majority. Two people prefer A over B. B's preferred to C by a majority, but C's also preferred to A by a majority. So we get a cycle here where we end up with majority rule. We have A beating B, but B beating C, and C beating A. So we can begin to see that there's going to be problems with voting rules in terms of making sure that everything's coherent in terms of the way that society is going to end up making a choice. And Condorcet cycles are going to be an important part of that. It's nice if we have a Condorcet winner. They don't always exist. So the next thing we'll be talking about is some of the properties of voting rules in more detail, and then some more general results on these things.